All right, welcome back, everyone. For the second session today, we're going to have Zahra and Junqiu, who are going to talk about physically based rendering and geometric simplification.
Hello, everyone. I am Zahra Montazeri, Assistant Professor at University of Manchester, and today I'll be presenting an introduction to physics-based rendering for the first part, and the second part I'll pass it to my colleague Junqiu to discuss more specific use case in relation to the field of geometry. Sorry I couldn't make it in person, and hope you enjoy the online talk and don't get bored, please. To assure that, I'm gonna start with some math. Ta-da! This is rendering equation, and it's a mathematical abstraction of how light interacts with the material in 3 dimensions. And it's probably the most important equation in modern computer graphics. It may look a little daunting with its vectors and integrals, but actually it's both simpler and sort of more profound than it looks. In this talk, I'll be breaking this down into the components, and then we're gonna look at each in relation to 3D scene, and then put them all back together again, so you can see how to use rendering equation as a tool to help you think about using computer graphics techniques to create graphical effects and photorealistic imaging. The idea that underpinned the rendering equation were described in 2 papers published at the same SIGGRAPH conference in 1968. David Emmel's research group from Cornell University described the techniques that we will look at this later today, and then it was James Gugger's paper, this one, that gave the rendering equation its name, the rendering equation. Both approaches used ideas that has been used in radiative heat transfer for quite some time, but the basic idea is fairly simple. All right, so now let's imagine we have a scene, the environment's like this one that has 3 objects in it. Let's say the red cube is radiating heat by taking into account the distance and the angle and a few other factors between the red one and the blue and green cubes. We can figure out how much heat has been transferred from the red cube to the other ones. Once the other 2 have received some heat, they'll radiate some of them back, which will affect each other. And the red cube and the cubes will continue to exchange the heat radiation until they reach out this kind of equilibrium state. And then if you can represent the heat transfer mathematically, you can figure out how heat is spreading around the environment, for example, by solving a load of simultaneous equations. And while it's been useful to do this kind of calculations about heat to figure out how heat is behaving in real environment, it was just until computer graphics came along that people got curious about how visible light is spreading. So basically, people didn't care about visible light exchanging in an environment. Notice here I'm being pleasably vague as exactly what I mean by heat or light or transfer, and in fact a whole bunch of other words that I'm using, but we'll get to all these precise in a moment. What the computer graphics basically did was applying the same sort of thinking from the radiative heat into the visible light, essentially asking the question, what would the scene look like if there were a viewpoint in there, which is the eye? The same kind of transfer of energy would be taking place between the surfaces, just this time would be modeling visible light instead of infrared heat. We would want to know what the steady state color of a particular point is. So we can paint out a pixel in an image plane. And that's what the rendering equation is trying to model. So that's the story of rendering. So notice this is the rendering equation, not just a rendering equation. And this equation describes all possible graphical scenes. And accurately calculating what the scene looks like become known as very tempting and challenging problem in rendering. But for a moment, let's just put this math aside and think about what it would mean to calculate what a scene looks like as the light interacts with a material. And let's see if we can construct the rough form of the rendering equation just by thinking about the shape of a scene. And yeah, we are going to stay again possibly vague about light and material as well, but we're going to get back to those terms as well. All right, let's take this scene as an example. Here, the camera represents the eye position, and trust me, it's less creepy than having a floating eyeball in there for all the time. We've got simple light point. We've got some objects in the scene. We've got a hard, shiny surface on the pool ball. We've got a transparent cube, gold mirrored monkey head, fractal broccoli, and fuzzy diffuse cloth on the floor. So now imagine we are looking through the camera into the scene. And I guess let's start by asking a simple question like, what would this particular point on the light source would look like if you have the image taken from the camera? Well, fairly obviously, it would be just white because the light being emitted from the bulb would dominate any other effect. And that's our first clue. Some points are themselves emitters of lights, and we would want to take that into account in our rendering equation as well. But what about if there is a point on the floor? It's not an emissive object. It's not a light source. This time, we don't have any light emitting directly from it. It's just some light bluish material of some kind. What would I see? Well, it depends on what light has landed on that point from elsewhere. Some of that light would bounces off at that point that we're looking into through the camera. It would interact with light detecting in my area in the back of the eye, and we would perceive the color. So that's basically the process. Now, in this case, the most obvious place where light would achieve at that point is from the light source. So we would have some white light landing on this bluish material, and then some of that would bounces off toward the viewpoint as a bluish light. So that's what we feel. And that's not the only place of light that we get from that point. The reason I can see the rest of the scene is because there are other light rays going on the other objects, although they are not emitting light themselves. So, but the light from the ball would land on the pool ball, for example, and then the pool ball would have some bounce off some part of it toward that point. So there's going to be some red light reflecting off that band on the pool ball, also some goldish light from the monkey, and a bit of green light off from the broccoli, and some purple light from the cloth on the floor. All right, now, in this case, the effect of all these other reflections on our point on the floor is massively going to be dominated by the light from the light bulb, but the other effects will be there. They'll be just subtle, but still they exist, but it's less obvious. Then these effects will make a more obvious differences if it's a reflection, because then we can see the interaction between materials more obviously. So just to recap, the color I perceive from this tiny point is when I look at it from a particular position, it's going to be some combination from any light that it emits from that, it's being emitted from that point, mixed with the reflection that comes from other objects in all other directions. And that is kind of intuition behind the rendering equation that we saw at the beginning. So let's go back to the math. We're not still fall asleep. This bit here on the left is the rendering equation with what we call spectral radiance. So that is the final color that we want to paint out our particular pixel in the camera. Arriving toward the camera from the point X, and here the letter omega O is the light in outgoing direction, and that O is for out. Surprise, surprise. Spectral radiance is a term from radiometry that takes into account the wavelength lambda as well as time for t. And so while this is closer to the physics of what's going on in the scene, the things happen over time, of course, like animation. And the light effects we see consist of effects of lots of combined wavelength. So, but for now, lambda and currently, the time, which is the parameter that appears on both right and left side of the equation, is just getting making the explanation a bit harder. So I'm going to cheat and make them go away for a moment. I'm just going to take them out from both ends and make them a bit simplified equation. So now we can focus on a simplified expression for rendering equation as this. On the left, we've got an expression that represents the light that I can see that arrives along direction omega O from point X. The first component on the right part is describing emitted light coming from point X, going along the vector omega O toward the camera or eye or an viewer. So this is the point that emits light because it's a light source itself. And then it's added to an integral. This next bit is an integral itself. And what we are saying is basically that for the full hemisphere, marked as big omega, we're going to add all different omega O that all contribute for different incoming directions. And then we have Li here. This bit over here represents the light arriving at point X from elsewhere. That is I for incoming again. Spoiler alert. So as you see, this Li is a recursion from Lo that comes from other points in the scene. So it's a intensely recursion process. We are going to add up the contribution of infinite number of incoming omega, because basically that's how calculus work. So we have different omega oi, and then that would leave these two bits aside. But now there's another part that we want to talk about, this bit, which is impressively named bidirectional reflectance distribution function. If you may already know about, this is BRDF. And it's an interesting enough function to have a little chat on it. We'll come back to it later in more detail. But for now, just treat this as a function that modifies the incident light coming in from omega I according to the type of the material, and then shoot it back toward omega O, which is the outgoing direction. And that should make sense how light reflects off a point. Depends on what the material is made of. Whereas if it's shiny or mirrored or fuzzy or whatever. So that's all on this bit. The final factor here is that dot product, which is the dot product of inverse omega I and the surface normal at the point X. What this says is we're going to attenuate the effect of the light coming along omega I according to whether the light is hitting the surface at 90 degrees, which will be the full effect, or toward the grazing. When it's coming at different angles, it's just grazing along, being parallel to the surface, in which case the effect would be close to zero. Basically, it doesn't have much light landed on that point in that scenario. So remember, the dot product of two vectors is the cosine of the angle between them. So this term here is really just a way of getting Lambertian's cosine law into the equation. If this incident light is completely parallel to the surface normal, then the angle between the normal and the incoming direction is 0. So that cosine term becomes 1. And we expect the maximum effect. So you see the light on the plane. But as we go further down, the incident light is getting perpendicular to the normal. So it's just grazing along the surface. The value of cosine is getting closer to 0, and we will get sensible values in between these two extremes as it gets less and less. Remember, omega I is not the single incoming vector. We have a combination of them. Omega I vectors formed by the hemisphere, which we represent here as a big omega. So there you have it, a neat explanation that describes what a point in the scene look like from a certain point of view. So that's all we need as a renderer, basically. And a rendering process for a realistic scene is often referred to as solving this rendering equation. But can we really do that? And the answer is, well, sadly, no, not really. Even having cheated and removed some of those detailed terms, you will still notice that we got an integral in there. And I've talked quite loosely about the infinite number of vectors from all around the hemisphere on that big omega. And that's fine mathematically, but we certainly just can't compute infinite number of calculations, right? So that leaves us with two options. The first is to find an analytical solution, that is to say, some mathematical jiggery-pokery that gives us a formula as a magic that would result that integral part for us. So that would be the basic calculus that can give us some handy expression to find out the area under the various curves. And although mathematicians have found out analytical solutions to several types of Fredholm equations of the second kind and whatnot, but sadly, rendering equation is not one of them. And part of the reason is because this is infinitely recursive. And incident light component, if they are not coming straight from the light source, it would arrive at point X because they've bounced off from other surfaces in the scene, and it's just possibly several surfaces. And quite of a challenge, which means we've have to apply the rendering equation for every single intersection. So we can't do that analytically, and we certainly can't do it with an infinite number of recursion calculations, because that needs simultaneous equations. So the second option is we have to cut corners. And that's pretty much modern rendering scientists are doing in a nutshell, figuring out which corners you can cut that gives you a decent approximation to the real value that we would get out from that whole thing on the rendering equation, and doing that in a way that you would pre-compute some scenes and you still have the decent realistic appearance. You may have seen it in movies and even in real-time games, and that would affect virtual environments, pretty much any virtual environments. And this is about a balancing trade-off between the quality versus performance. So this is why we started this talk, to have a trade-off between geometry simplification and a sophisticated rendering, which my colleague is gonna take care of more specific use case in more detail, but that's as in a high level why what we do as a rendering field. So let's see, when light interacts with a material, there are three things that can happen. The first is that the light is reflected, which can appear as mirrored or shiny surface with specular highlight, or it can be transmitted through the surface, which we'll see as a transparency or reflection, or light might be absorbed by the surface and converted it to heat. In fact, what we see is usually a combination of these three. But first, let's look at these effects in more detail, and also how we perceive light and how we perceive color. And we will tie this into the BRDF that we explained at the beginning. Let's just start with reflection. If the light hits the surface and is reflected off in a single direction, or at least in a very narrow range of directions, we will see a mirrored shiny surface. Light bounces off on a surface is exactly in the opposite direction. So that's why we see a reflected image that looks as though it's the same distance on the other side of the mirror as the viewer looking at it. So that forms a perfect mirror. Mirrored surfaces tend to be metal and the same mobile electrons that allow metals to conduct the electricity tend to basically put down the electromagnetic radiation. So that's why we have the exact radiation that goes from one direction to the other. And as long as the material is smooth and flat, that means the light will bounce off in a well-defined direction in the same way that a tennis ball would bounce off on the wall. So that angle of the incident is the same angle for the reflection. And that means both the color and the shape of the image are mostly preserved. But diffuse reflection, on the other hand, is when an incoming light scatters off in all different directions. Here, what's happening is the light is penetrating the surface a tiny bit, and then it's being reflected back out. It might look flat, but actually it has a lot of fibers in it that cause the scattering. And when the light interacts with those tiny bits, it bounces around a little bit before it re-admitted, and the direction gets messed up. So instead of coming out in one coherent direction, like mirrored reflection, it's basically pretty much all over the place evenly. And another possibility is something in between these two, when incoming light bounces off mostly in one direction, but not exactly in one direction. And this would give us a hard shiny effect. And we would probably see a bright specular highlight, maybe even a little bit of a reflected image, but not the same as a perfect mirror from the first slide. And if you look around you, you will see that a lot of surfaces have some combination of diffuse and the specular reflection, which would look like this. Quite a lot of scattering of the light happens, but some elements of a specular reflection as well. But of course, in real world, things aren't a bit tidy as what we saw. No surface, not even polished mirror, are perfectly flat like the ones that we saw at the beginning. And the perfect Lambertian diffuse reflector, the even distribution one, where the light gets scattered off equally in all directions, just doesn't really exist as well. So in reality, surfaces are much more uneven, and that means the profile of how light reflects off them is much more complicated, and that complexity is what the BRDF is trying to model. So again, I want to jump ahead for the talk that we have after this. What we are particularly talking about in the next talk would be different BRDFs, particularly for cloth. So you see how we can simplify the geometry to just make use of the appearance, essentially, by sophisticating the BRDF. Yeah, that was a spoiler alert to the next bit. But before we learn about BRDF, I want to spend a moment just talking about our perception of color. We see color because light enters our eye through the pupil and lens in our eye. And after passing through some clear jelly-like stuff, it hits the retina at the back of our eyeball. And that's covered in light-sensitive cells or receptors. And as a human, we've got trichromatic vision. We've got 3 different types of light detector cells that are sensitive to red, green, or blue light. And you might notice here that there are 4 more red receptors that either blue or green, that more about in a moment. So in combination, these red, green, and blue receptors allow us to perceive a certain range of electromagnetic radiation that we call visible light spectrum. And there are other creatures that have different types of light receptors than us as a human. They experience light in a very different way. So it's not that there is anything fundamental about this range of frequencies that we are calling visible light. It's just that a bit of electromagnetic spectrum that we happen to be equipped to detect. So if we plot the response curves for different light detecting receptors in the human eye, it would look like this. These are normalized response curves. So the unit on the y-axis basically doesn't have any unit. It's just varying between the maximum response and 0 or none, no response. There is quite a lot going on here. One thing, for example, you may notice that the curves aren't labeled as red, green, and blue, and they are S, M, and L, and that's short for short, medium, long wave responses. This relates to the wavelength ranges that our cells detect, rather than the color specifically. And that's because red, green, and blue don't really exist in physics as such. They are just labels that we give to things that we perceive. So in this case, small ranges of visible light spectrum, medium and long. You will also notice that the curves aren't evenly distributed across the spectrum. The medium and long curves for the cells that detect greenish and reddish light, they are bunched pretty close together, while there's a big gap between them and the peak of the short wavelength detector. Although we really don't know exactly why that happens, a reasonable guess for this is that humans have evolved to be good at distinguishing between red and green. To detect subtle differences in those colors, it really mattered for us to have more receptors. We don't know for certain, but of course, spotting a tiger in the middle of a foliage, or when you want to pick up a fruit from the tree, or some other examples, it was quite survival trait to distinguish between these two colors. Whereas the sky is just big sort of blue thing that's not that interesting to have that much of receptors to waste on. So that's probably the story of the wavelength, and enough background for us to be able to talk about BRDF now, which is the bidirectional reflectance distribution function. So this BRDF was first described by Fred Nicodemus and colleague in this paper, and it's not an easy bedtime reading, trust me. But essentially, in a very simpler form, the BRDF is talking about the ratio between radiance and irradiance. And although very loosely, this is a bit like the ratio between reflected of the incoming direction. Radiance and irradiance are specific terms from radiometry. That's the field of measuring electromagnetic radiation, and they have a specific meaning. So it may look a bit fancy, but that we're using the same terminology. So here's the Wikipedia definition for radiance. In radiometry, radiance is a radiant flux, and that's just energy over time. That means energy over time. So that's not too bad. So far, so good. Emitted, reflected, transmitted, or received by a surface. So here's the kicker. Per unit solid angle, per unit projected area. So that makes the math of BRDF a little bit hairy. It's grounded in a way of measuring things that is standard practice for radiometry, but it's a bit weird if you are not used to working in spherical coordinates. So in one level, it's not too hard to get your head around it. We are talking about measuring things in terms of altitude. That's an angle from ground lane up and down, whereas the angle between the particular defined angle for going left to right is azimuth. And the projecting shape onto the curved surface of the sphere or hemisphere, and then maybe back onto a flat surface of a plane. But if you're not used to doing that, it may seem quite complicated. So let's try to unpick this a little bit. Let's take our hemisphere, our usual point X, and regular 3D coordinate system. The different components of BRDF refers to an incident ray omega I, and then we have reflected ray going toward omega R direction. So these are both parameterized in terms of phi, which is the azimuth angle, as well as theta, which is our altitude. So a BRDF then does the calculation in terms of a delta solid angle in the plane and the projected of that solid angle onto a delta projected area on the surface of the hemisphere. So putting the spherical geometry and delta stuff aside for a moment, if we think about what this actually represents, it's not that bad. So this is what we need as a delta angle to calculate the BRDF. So maybe casting it may maybe be more familiar. What we are really talking about is how we evaluate a BRDF for a given material. Different types of material is this. For example, a light arriving along a given direction vector, omega I, striking at point X. But now, how much of that incident light or incident energy is reflected specifically along a particular outgoing vector, omega O. Here I'm using magnitude of omega O to represent the output of the BRDF. So it's basically the length of vector as a proportion of the incoming light vector, okay? So remember we magicked away the lambda some time back? Well, here we can bring it back. So to make this more concrete, imagine we have a light of wavelength 625 nanometer, and I'm just going to call it red light, and that's coming in direction omega I from the light source. Evaluating the BRDF for this material would tell us how much red light is heading out, specifically in the direction of omega O. And we could do this same for the green light as well as blue light. And then we would get different values, probably even if we kept omega I and omega O the same, because the most material responds slightly different to different wavelength of light. So that's pretty cool. Combining these, we would be able to say something about what the point would look like if viewed from a particular direction. So hopefully that would demystify the BRDF a little bit, so it's not a mystery anymore. We've reunited now our rendering equation with wavelength term as well. So this BRDF bit is what we now discuss. So that's the radiance that we talked about. That would be the output of this function. So a BRDF, to clarify, is just a function that has defined set of inputs, and that gives a result that has defined meaning. In actual math, that goes on inside the BRDF. So we can basically represent any sort of material. You could have a BRDF that just returns 0 for all possible inputs. That would effectively be saying, regardless of what kind of light comes in any direction, and regardless of what angle you are looking at this material, the answer is no energy comes out. And that would be a blackest of all black surfaces, something that would eat light, essentially. So that's the extreme BRDF. Or you might write a BRDF that says, whatever comes in goes out. Or you might perturb that in a little bit and make the effect more complex and more interesting. So then you're the king of appearance. But so far, we've talked about the BRDF as a theoretical thing involving material, light source, viewpoint, sensor. But if you want to measure the BRDF in real world material, you will need something like this. So this is the goniometer. This kind is from Toulouse Aerospace Lab, which has got an arc that holds the light, and the sensor you should basically move so you can go around different angles and you have a turntable, so you can sample the material from different directions. This rather more compact one has a dome on it with multiple fixed light sources, but it achieves the same thing, the same effect. The kind of results you will get from these devices that's represented in a picture like a volume rendering. You can see something like this, where what happens to the light when it hits particular point X. They give an idea of what real-world reflection profile looks like. So for a single frequency of light, you can see they are much, much more complicated in shape than our simplified Lambertian evenly distributed BRDF that we just saw, okay? So to summarize then, light hitting a certain point on a material might reflect off in a specular spike, and it might scatter off in other directions as well. And that's what captured by BRDF. And you've probably spotted by now that reflection is only part of the story, because of course some materials allow light to travel through them, and that would called transmission of light. As light passes through the material, it probably going to be refracted in accordance with Snell's law, and that makes that to be parallel with the top one, but an offset as it emerges from the other side. And maybe it stays in a coherent beam, or maybe it scatters off. And so this is all would be defined by BTDF, essentially, which is bidirectional transmission distribution function, which thankfully is basically the same kind of idea as BRDF. Is just for light emerging from the other side. So nothing new, it's just the same thing on the opposite direction. Then, when the light hits a translucent surface, rather than being reflected or transmitted, it might go a little bit bounced inside the material before it escapes back out at a different point. This effect is called subsurface scattering, and actually most non-metallic surfaces exhibit this to some extent. We have so in few cases, like skin or icing on a cake, they are much more visible. So this is the picture of my colleague's hand. We have a backlit on the back of the hand with a quite bright light. The bits where you can see between his fingers are just the light coming straight through, but the red glow you can see between his fingers, that's the subsurface scattering thing, where the light is bouncing around inside the top layer of the skin, and then it leaves the medium from some other part. So you can see this effect in rendered images as well. So for example, this rendered image of Suzanne monkey is without a subsurface scattering. So this is pretty much look like a flat clay monkey from Blender. But this one is with subsurface scattering on. It's the same material, just with subsurface scattering refraction enabled. You can see how realistic it becomes. You can see the effect most obviously on the ears, as well as human ears, actually, in real world. But you can see it more subtly over the whole model because it's thicker in the middle, but it becomes instantly more realistic. So, and the final thing you may encounter is BSDF. That would be the bidirectional scattering distribution function. And this is a general term for all the functions we've looked at so far. It doesn't have a precise definition in the same way as others do. It's just probably being used as a as a tool for the combination of BRDF plus BTDF plus BSSRDF. So that would be the bidirectional distribution, scattering distribution function. All right, so that concludes what I've been trying to include in the introduction of rendering. Hope we have few of them awake and you're ready for some questions. This was part of the course we teach at the University of Manchester. So I got the credit to my colleague Steve Pettifer as well. And I'm now ready to take some questions.
Thank you very much for the nice presentation. When light enters the material, it most often changes its wavelength, but in the rendering equation that we have seen so far, we have only using one wavelength. How do we accommodate this change in wavelength in the rendering equation?
Okay, thank you. Good question. So that means we got some people listening. I appreciate that. So we removed the omega at some point over here, just for simplicity. But imagine in reality, we would have different radians per wavelength. So we have to do like 400 of these calculations for all different wavelengths and then add them up to find the actual average. But we basically don't do that if we don't have the need for spectral rendering. And to best of my knowledge, there are not that many production renderer out there that does spectral rendering when you can actually see the rainbow. So we pretty much do it for RGB. So that's what we typically do, 3 equations added together rather than 400. Even the ones that I'm aware of at Weta, they do like 80 pins instead of covering the infinite wavelength, because of course it's an infinite spectrum.
Okay, thank you very much. Yeah. Would this mean that we have to integrate over the wavelength in between the rendering equation where we integrate over the hemisphere?
Exactly. So you are doing the same thing per wavelength, and then once you have the radians for each of those wavelengths, you have to average them out in order to get, or if you want to represent it, if you have the viewer instead of an RGB PNG format, you have a spectral output. So it has more than 3 channels. For RGB, it actually has 80 channels. So then you would assign every channel to be its own color. So once you see it, it appears as a rainbow. So those are called spectral renderers that can do more than 3 channels, which is the most common version of renderers we do.
Okay, thank you very much.
Thank you. More questions? I'm ready to be grilled.
This is hopefully a pretty simple question. I was just curious. It was really cool to see those BRDF visualizations. Do you know like what materials those are for some of them? Like there were these ones that had this, I don't know, sort of like a plume-like character, like sort of, I don't know. Some of them seemed pretty clear. There was like, you know, a sharp specular and then like some diffuse stuff, but there were some that looked more exotic. And I guess I was just curious what materials those were.
Good question again. So I would first start with the cloth laying on the floor modestly to just again give you a heads up for the talk by Junqiu after this to have a particular cloth material. So fabrics in particular are quite complicated. You cannot have a combination of a specular and diffuse to make the cloth look like cloth. So I'm gonna save that for her bit to see what other BRDFs or BSDFs you can define to make a cloth look like a cloth. But the other two, for example, the gold monkey is a metal, or the broccoli is some rough dielectric. So if you have heard of microfacet distribution, for example, that's something similar to what we saw in this slide, which is somewhere in between. So there are some microflakes going on. There are some translucency as well. So it's quite complicated that we have both BRDF and BTDF going along those transparent materials. So those are more complicated materials, but they can be represented with their own BSDF.
Okay. Yeah, I was actually asking about like the slide. You had like a visualization of like the BRDF capture results. Like if you could go to that slide.
BRDF capture, you mean like this one?
No, you had like there was like the big machine with like the rotating table, and then the like sensor captures, and then there was a sort of a smaller version, like a modern version that you showed, which was like some sort of, looked like it was sitting on some sort of like optics table.
I'm not sure. Maybe I was sleeping. I don't know which slide you're talking about.
It's okay. I mean, we can move on if it's fine. It was just, there was this, you had that cool visualization of sort of like the, it was a function on a sphere, right? And it was sort of showing like.
It said slide with a corneal
The slide with the, what, sorry?
corneal reflector.
Oh, the corneal reflector apparently is what it's called. Or.
The real world measurements, right?
Yeah, we were asking for the measurements.
Oh, got it. Okay. So these are the.
Yeah, this. I just thought this was super cool. Yeah, like, and I was wondering if you could tell us like what some of these materials were.
Yeah, these are, I don't recall the names for these materials, but they are different plastics because they are all reflections. We don't have a transmission on the back. So the broccoli that I showed, it had a bit of translucency, but this one, for example, they are all reflections. So you can expect these to be different plastics. But I don't know the particular model that they've used, but this is some sort of reflections, measurements that what happens to the light, what happens after it hits it. But what I can assure you is they are all reflected, which is less complicated than the ones that we have also the transmission, which again is going to turn up soon with the next talk.
Cool, thank you.
You're welcome. Thank you.
Hi, in production renderers, is the state of the art still just super sampling ray tracers massively?
Well, thank you. Good question. Of course not, because one solution, if you have fancy BRDF like this one, the ad hoc or easy method is to super sample it. So you can basically cover the whole BRDF by shooting hundreds or thousands of rays, which is not practical. And there are a lot of approximations that we can do. For example, can we guess where the majority of the samples would affect the most? So then we can focus on that. So then we have this PDF, the distribution function, the probabilistic of it, that gives us a kind of intuition of what the material looks. So then we can shoot the samples smartly. That means sampling smarter rather than harder. So then we have some bias toward the directions of samplings that we make in order to save more samples. So that's one easy way that everyone does, which is called importance sampling. It means that we are shooting samples toward the parts that are more importantly for us, which is a total discrimination. And there are, of course, all other methods, but hope that clears off.
Thank you very much for the talk, Professor. I had more of a philosophical question. So, because you're being very nice to give this talk at this geometry conference. So when we deal with geometry or like physics simulation in geometry, we often don't start that much with the real world and say like, here's the real world equation that we want to solve, and then like our job is to go from this equation. But sometimes we say, we just want things to look pretty, and we could go the real route, and that maybe is very hard. But some of the talks we had yesterday, for example, were more like, here's what seems pleasant to humans apparently, and it turns out that's much easier to do than the physical equation. So I guess I'm asking, within rendering as a field, which one of these is you feel more predominant, or are these the same specifically in rendering?
Thank you. That's actually a very good motivational questions, because why should we care to do a fancy rendering if we can geometrically be faithful to what we model? So then that would turn up properly. So I showed some materials have some micro details in them, and that actually causes to look like this. And if we have a proper geometry, for example, down to the fiber level, then it would come for free. So that's a very valid question. But the short answer is for practicality, because I know that making a proper geometry would ditch the whole rendering altogether. But having that fancy geometry in the first place is not practical at this era. So what we do as a trade-off, we simplify the geometry, which is our bottleneck, and make the rendering sophisticated in order to compensate what we have simplified on that. So instead of having the microfacet model, of course, the microfacet model, if people may have heard of it, have all those micro flakes in it. But we would just assume there is a flat surface, and then instead, during the runtime, we add those details on to make the rendering complicated for the sake of simplifying geometry. So that is the trade-off to compensate the loss of detail in real physics to be handled in our hacky graphic way.
Thank you very much. So I guess the answer is that you do the real physics so that us in geometry don't need to do all the hard work. That's a very diplomatic way of saying that. Thank you.
And by the way, you're welcome to the geometry community. We are taking care of bottleneck mess that you leave apart.
Thank you, thank you. We're a little tight on time for Junqiu's talk, so I'm sure Zahra is welcomes questions over email, or you can reach out to the second speaker too. So now we can move on to the second part about geometric simplification. Thank you, Junqiu.
Thank you.
Thanks to Zahra. Now let's go to the second part of this course, physically based rendering of cloth related to geometry simplification. Cloth rendering has always been an important and popular research topic in the field of computer graphics. Its applications are extremely broad, including entertainment like clothing in games and movies. Recently, the rise of mobile VR devices and digital human technology has created high demand for realistic cloth rendering. So the online retail, like the mobile terminal sales and virtual fitting rooms, also require accurate cloth rendering. Solving the problem of cloth rendering is an urgent need in both offline and real-time rendering domains. Today's course is divided into 3 parts. First, we will cover the basic knowledge of cloth, including the geometry of the cloth and its optical complexity. Then I'll dive into the methods for cloth rendering and modern cloth rendering topics. Now let's start with the basic knowledge of cloth. When we talk about the complexity of cloth, we focus on both at the far field and near field. So when we look at the piece of cloth, it has a unique sheen and texture. But under a microscope, we can see a much more intricate structure. Cloth are made up of thousands of short fibers twisted together into a continuous strand. Cloth have their own weaving patterns, twist levels, and other geometric features. So these characteristics determine how cloth looks like under different lighting conditions, affecting its optical properties and how this cloth looks like. So if we zoom in further to the level of individual fibers, each fiber's microstructure is defined by its shape and the optical properties. These tiny fibers, usually between 10 to 100 micrometers, have key features like their absorptions and refraction indices. So we could also see the titled scale on the outside of the fiber, which will influence the direction of light reflected and transmitted. How these fibers are arranged and their surface structure greatly influence the scattering and the reflection of the light, so which impacts the overall appearance and feeling of the fabric. And when we are rendering fabrics, we need to analyze those geometric and optical characteristics in detail. Only by accurately simulate these macrostructures, we can truly capture the fabric's realistic appearance. This involves precisely modeling and the rendering details like the twist of yarn, the weaving patterns, and the arrangement of the fibers. By doing so, we can achieve a highly realistic fabric rendering effect. Now let's see the common structure of cloth. So cloth has a complicated structure at different levels. It is commonly made either by weaving or knitting techniques. But so far, most of the studies in cloth rendering have focused on the woven fabrics because they have a simpler structure. And many real-world yarn consists of, we can see from the top. So many real-world yarns consists of the multiple substrands, or we call it plies, which with each ply containing hundreds of fibers twisted around our central axis. The yarn structure can be generated procedurally or match the real samples. So for woven cloth, the layout of yarns is described by a wave pattern. Parallel threads called warp yarn are interlaced orthogonally by another group of parallel threads. We call it weft yarns. So the wave pattern can be represented by a two-dimensional binary matrix, which defines for each crossing point whether the warp or the weft is visible from above. And another very important feature for the cloth is that it has diverse and unique appearance. For example, for the knitted fabric, we can see the vertical highlights forming a connected line accompanied by another column of discrete diagonal highlights. We call this schematic highlights. And if we put a light source behind the woven cloth, we can see a cross-shaped highlight. So the cloth can also exhibit a transparent effect. For instance, the window gauze appears very thin and transparent feeling. But the cloth rendering is very difficult. First is because of the huge number of fibers it contains. To achieve the realistic representation of a piece of clothing, it is necessary to model the geometric properties of all the fibers. However, creating the geometric representation for each fiber level in a complete garment can be extremely memory intensive. For instance, modeling all the fiber geometry for a pair of jeans would require approximately 3 to 5 terabits of the memory space. Moreover, the abundance of the fiber presents a complex multiple scattering, and the increased number of light bounces leads to a slower rendering and difficulties in achieving convergence in the rendering results. In addition, the appearance of cloth is even more difficult because of the complex different level of geometry. So the multiple scattering in a yarn is complex, which makes it difficult for the rendering result to converge. Also, due to the complexity of the geometric structure and fan arrangements, it is challenging to derive the correct aggregated shading model. Now I will introduce some the traditional and classic cloth rendering model to show how they render cloth. So the cloth rendering methods can generally be divided into two categories. The first category is based on microappearance. These methods require modeling the finest fiber geometry and rendering the detailed geometry which overlaps with the CAD-CG area. They precisely render multiple scattering and will conduct to a very realistic appearance. So the second category is surface-based. This method is very simple because they only need the surface geometry and some texture maps as input. So I will first introduce the microappearance methods. The microappearance methods need to model the most detailed geometry level, which is the fibers. As we introduced before, there are 3 levels of cloth geometry: fiber, ply, and yarn. So Zhao et al. Proposed a microgeometry modeling method of cloth can be synthesized procedurally. This approach offers the advantage that a model-driven architecture allows for intuitive editing paradigms. They consider a yarn consists of regular fibers and flyway fibers. Model parameters may be described in such a way that they resemble parameters familiar to experts in this field. In the context of cloth, this could be a certain description for weaving patterns, the twists of fibers and plies per centimeter, or optical properties of fibers. So with the regular fibers handled, the remaining task is the flyway fibers. Flyway fibers are really important for the visual realism. So because we can imagine without them, the clothes will look too perfect to be real. We can see from this video, this method can model different yarn geometry by easily changing the parameter. After we have the cloth geometry, we need to derive the cloth shading model, specifically for single fiber. Light scattering from individual filaments is the basis of physical accurate rendering of cloth. If the internal structure of a filament is known, a full geometric representation of individual filaments is possible in principle. The appearance of fiber is typically dominated by 2 features. So first is the strong, distinctive, and tropic highlight, and the translucency. Both effects are well understood and can be explained by analyzing the cross-section shape and optical material parameter to the fiber's interior. To conclude, the microappearance accurately model the fiber level geometry and achieve the realistic rendering. So by combining the detailed geometry modeling and an accurate fiber shading model, we can achieve incredibly realistic rendering results. We can see they really match the real world good. And however, there are some limitations. So one problem with the explicitly modeling fiber geometry is that up to billions of fibers are needed to create the large cloth. A straightforward solution to this problem could be instancing. But this only works in a limited number of situations. So because even for repeating wave pattern, the geometry of yarns usually don't repeat with the same frequency. This is because the cloth is soft material that can dramatically deform, resulting in stretching and squeezing of yarns. Additionally, the fancy yarns may have spatial variances along their length, contributing to the specific look and feeling of clothes. It will contribute to the glint appearance we look. So then after we introduce the first category, let's go to the other category, surface-based cloth rendering. These methods only need the surface geometry, or we can see the triangles. And the simplest approach to modeling a cloth is probably using a combination of the surface, texture, and normal mapping. However, this approach fails to model the anisotropic highlight and the effect of multiple scattering, so it is only used for very simple real-time rendering. An initial improvement is to store the tangent directions of fibers. In addition, texture maps and use anisotropic shading models. And now I will introduce one of the most famous surface-based approaches to model the appearance of woven cloth using BRDF and BTDF at the yarn level. That approach was presented by Irawan et al. They defined the wave pattern with parameters that include warp and weft distribution, the twist direction of fibers, and the curvature of the yarn. And also they derived a shading model to simulate the fiber BCSDF level on the surface. The result, we can see which are validated against the measurement, yield visually plausible results from a wide range of fabrics. Unfortunately, some of the model parameters are based on ad hoc assumptions, and they cannot be directly inferred from the optical fiber properties. And another drawback of this method is that it can only represent the surface reflection without considering the transmittance. And another very important model is Sadehi et al. They present a far-field model for cloth. So they formulated a light scattering model for threads, which was validated against the measurements of individual threads. A wave pattern is used to model the converge of different thread types, their tangent directions, and to obtain the shadowing and masking term. And here we show the result. So this method is the most fast one of the surface-based model, and those results are comparable to the real cloth samples, but they lack of the near-field details. So if we zoom in, we cannot see any details or the wave patterns. And also they look too thick, because this method also can only represent the surface reflectance without considering the transparency of the cloth. Now we conclude the surface-based method treat cloth as an explicit surface like mesh, and primarily encodes its appearance through reflectance model or scattering at a given point. For example, like these previous works. The advantage of such methods is their speed and lightweight nature, as they treat cloth as surface and do not consider the complex geometry and multiple scattering within the cloth, so they are memory and time efficient. However, these methods have clear drawbacks. So first of all, the lack of the realism and result in a flat and opaque appearance. Additionally, efficient surface-based models rely on assumptions specific to woven cloth, make it challenging to handle the knitted cloth. So we can see the key problem of cloth rendering methods is that they are struggling to the balance between realistic and efficient. The macro appearance methods can produce very realistic results, but they are slow and require a lot of memory. On the other hand, the surface-based methods are very efficient, only needing the surface geometry, but the results are not realistic. And an ideal rendering model needs to meet those several requirements. First, we need it to be accurate and realistic. We want it to be physically based and as real as photos. And the second, we also hope it is fast in rendering and efficient in the memory. And also, it should be general to include both woven and knitted. So how can we achieve this? Based on our analysis of the difficulty of cloth rendering is derived from the complex geometry. The first step is to reduce the number of fibers. This is key to solving the memory and the performance. And the second, while reducing the number of fibers, we want to maintain the realistic appearance, which requires us to aggregate the fibers. In the recent 5 years, modern cloth rendering methods have been proposed to solve the problem of realistic and efficient based on the concept of appearance aggregation. First, I will introduce why do we need to aggregate appearance. So take a look at this hemisphere. When you zoom in, you can see the individual fibers, but when you zoom out, you can only see the overall appearance. This means for the very complex geometry with a lot of details in the far field, we can simplify the geometry. But if we simply reduce the number of fibers, and in order for the results not to appear too sparse, each of the remaining fibers will be simply thickened and keep the original shading appearance. So as illustrated, the rendered appearance is almost completely different to the original. But with the appearance aggregation, the simplified fiber geometry could match the ground truth. Appearance aggregation means the summarizing the intricate details of the appearance into a simplified representation. So this process can enhance the rendering efficiency and performance without scarifying visual quality. This is a problem that combines both geometry and rendering. We need to simplify the geometric complexity while still ensuring that the rendering looks good enough. As we mentioned earlier, the biggest problem with appearance model is that the large number of fibers. So the basic idea is to model the cloth only with the ply or yarn geometry, which reduces the complexity. However, we still want to see the details of the fibers. So Montazeri et al. Proposed a ply-based cloth model. The model only needs the ply geometry as input and has fiber silhouette. So they aggregate the fiber interactions into a ply level model using 4 lobes. This makes the rendering quite fast. Comparing with the ground truth, which accurately model the fiber geometry, the ply-based method with fiber details and flyway fibers can generate a very close result, but only requires about 3% of the memory. Here we show the ply-based method. It can produce a very satisfying rendering result, and because they only use the ply geometry, it makes the rendering quite fast. However, this method has some drawbacks. First, it is artist-driven instead of physically based, so we cannot derive a ply shading model directly from the fiber. And also, it is not efficient enough for the multiply yarns. And another curve-based method is the yarn-based. So this method needs yarn as input and can divide it into 2 parts. The first part is geometric representation, which can represent the ply level geometry by using a proposed implicit tracing method of the yarn. And for the shading part, this method can accurately aggregate the light scattering, which is physically based. Now I show some results. So comparing to the yarn-based model to the fiber-based yarn, and even we change the geometry parameters such as different density. Fiber twist angle can affect the yarn appearance, while this method can successfully reproduce both geometry and shading. Here we show the rendering result of this method on the knitted globe, including both far field and near field observation. So in the far field, shown on the right, the proposed method closely resembles the reference, and the differences are hardly noticeable. However, in the near field shown on the left, this method does not visualize the fiber geometry explicitly, yet accurately capture the overall appearance by taking into account of the fiber statistics. And an improvement of the yarn-based method this year is Carter's work, which enhanced the implicit yarn tracing to achieve a more precise ply geometry representation. And they add fabric details on the ply, which makes more realistic near-field rendering. They also improve the shading model and derive a multi-scale shading for the yarn. So let's conclude the improvement on the curve-based methods. They are efficient and accurate and can represent the analytical solution for single and multiple scattering of light at the yarn level. The yarn-based model incorporates the hierarchical geometry to account for the physical properties of the yarn, ply, and fiber. Furthermore, unlike the previous works, those models are general and can be applied to render both woven and knitted fabrics. However, this method is still curve-based. Despite these accelerations, it still needs modeling the yarn geometry as least and handling the multiple scattering between the yarns. So a natural question is that, can those models be more efficient both in memory and performance? The answer is the surface-based model. The surface-based model are the most efficient because they don't require modeling curves or tracing the multiple scattering between the curves. Zhu et al. Proposed a surface-based cloth rendering model. So they bypass the curve geometry and only uses surface geometry, yet successfully maintain a realistic cloth model. All they need as input is a mesh with only 4 textures, and they first derive a macro-scale model that describes the reflection and transmission at a single point on the cloth, and then they derive a meso-scale model to tell us how to shade an entire pixel. This model is fast in rendering and only require minimal storage. And also the most important part is it is very realistic. It can represent the different type of fabrics and is able to model the complex visual effects of cloth, while other surface-based model can only represent the asymmetric highlight. And also this method has successfully applied to the Meta's products, and it is now the official cloth rendering model of the VR device now. So in this video, the surface-based aggregated model shows a realistic rendering in both near field and far field. However, in this video, they use about 1 key SGP to avoid alias because they still rely on the sampling to solve the integral of a pixel. At the far field, when we shade a pixel, and it requires to account for by every pixel within the pixel footprint. Also, they use uniform BSDF sampling, so their method is not efficient, especially under the complex lighting conditions. And this year, they propose a multi-scale rendering model in O1 complexity. For the multi-scale rendering, we want to answer one question: how to integrate the pixel without sampling. So let's see this equation. This is very complex situation because the cloth is closely related to the visibility. So if you want to consider the position, the integration over a pixel, we need to consider the position, incident direction, and outgoing direction, which is 60. What they do is they part this integration into 2 parts. So for the first part, they solve the integral without considering the visibility. Now this can be reduced to a 4D. They use a glint-like solution, and for the rest part, they use the idea of contravariates to deal with the visibility. Here is an example for the real-time rendering to show the multi-scale rendering strategy works, and the rendering time is only about 8 milliseconds per frame. Although the current surface-based cloth rendering model is as efficient as real-time and as realistic as photograph, there are still some limitations prevent it to be perfect. The first one is the flywheel fibers. So we can observe that on the rest image. The flywheel fibers greatly enhance the reality of the cloth rendering. However, current surface-based methods cannot model these individual flywheel fibers, and it's even more harder to propose a multi-scale model. The second is current methods can only take the repeated pattern as input, while the actual cloths are very irregular, both at the weave patterns and migration of the yarn geometry. And the third is the multi-scale method can achieve real-time rendering, which is a good thing. However, it relies on a heavy pre-computation, needs more than 10 minutes for each kind of cloth. It is necessary to design an editable method without pre-computation. So these limitations should be addressed in the future. And thank you very much.
Thank you. This is really nice work. The previous slide, is that a photograph or is that a rendering?
This is one of the rendering.
That's the rendering?
Yeah.
So I'm looking at the edges of the shoulders and we can kind of see some flyaway fibers, it looks like. Is it actually modeled or how is that done?
Yeah, so this is a rendering using the micro appearance method. So they actually model the flyway fibers on the shoulders.
As actual geometry?
Sorry?
As geometry?
Yeah, as geometry.
Wow, that's very impressive.
So for the flying fiber, do you only have to model it on the silhouette, or does it have an impact on the surface itself?
Excuse me?
I mean, the flyaway fiber, we see it on the silhouette, right? So but computational wise or visually, does it also have an impact on the plane surface?
Yeah. They model the flyway fibers on the whole the shirt, and so it also causes the feeling of irregularity on the surface.
Okay. Mm-hmm.
Yeah. Thank you.
This might be a little more of a philosophical question, but how does one judge the realism of rendering? Is this an empirical question? You know, play Turing test, show people different models and ask them which one's real? Or what's the approach?
Yeah, thank you for your question. I think that's also the same purpose, like the geometry simulation. And I mean, we want to finally we want our rendering. We cannot tell the difference of the rendering and the real world. And so the previous methods are too perfect. I mean, we have some defaults on the rendering. Some defaults on the actual appearance we can observe. But the previous methods are too smooth and they lack of the details. So the current or the fancy rendering topics are focused on the details, and that makes the rendering more realistic, and that's my answer. Thank you.
Just wanted to follow up on my compliment. Actually, Alder Ray Smith, I think, said that reality is a convenient measure of complexity. So maybe that answers the question of what looks real. But I just wanted to put my compliment in context. I mean, back in the 90s when we did Final Fantasy, we slapped an anisotropic shader on RenderMan curves and we thought we were done. So this is pretty amazing.
Thank you.
Well, we can end on that note, and we'll see you all at 2 for the next part. Thank you again.
Thank you very much.